Okay guys, my video keeps getting interrupted, so I'm going to go through this kind of fast. It's the third time I've started. Today we are building a characteristic equation for a real life example. I've chosen an example I'm familiar with. We have a discharging capacitor equation that we want to build. We're going to pretend that we're the first people on the planet to ever write this equation down on paper. We don't know what it is. We do know that its voltage and its current changes over time. We want to be able to have an equation where we can plug in a time and figure out its voltage at any given time or any moment. So we want to know how this thing discharges. Does it discharge like this? Does it discharge linearly? Does it discharge like this? Is it something weird? Okay. We're going to build the equation. I've redrawn the transfer circuit here. We've gotten rid of the source and the switch. We're assuming that this thing is already charged and the current is running in this direction. Okay? Conventionally, positive to negative. So we're going to have to use Kirchhoff's voltage laws. We're going to start here at ground. We're going to say plus VC plus VR is equal to 0. I already have that written down for my last attempt. So plus VC plus VR is equal to 0. And we're going to solve it for VC. We're going to say VC is equal to negative VR. Okay? At this point, those of you who like to play with circuits and stuff, and you're beginners, it just kind of seems like you're getting off topic. Okay, but we're not, because this is going to be important. We're going to write some relations down, then we're going to see how they unfold. Okay, so what is VR? VR on here is I, which is the current, times R. Okay, so that's pretty easy. I times R can be replaced right there in the equation. So what is I? Let's figure out what I is. I is changing over time. Okay, so I is changing over time. So that is the capacitance multiplied by the voltage of the capacitance over, or the change dVc over the change in time dt. Okay, so that's what I is. I is the capacitance times the change in Vc over the change in t. And these are differential chunks, instantaneous amounts. Still can't do nothing with it, basically. So we're going to keep working this down. So let's just rewrite this. We have Vc is equal to minus R, that's the resistance, times the capacitance times the differential change in the voltage of the capacitance over the differential change in time. Okay? So this is I, this is R, and the whole thing is negative VR. We haven't changed anything. VC is equal to negative VR. So we're still in the closed loop Kirchhoff's voltage law right here. So now we got to kind of separate these two so we can get rid of them. So the first thing that we have to do is we'll just bring the dt over. Okay? No, we'll bring the VC over. Okay, so let's stay on topic here. So VC multiplied by or divided by dVc. So it's the voltage of the capacitor divided by the differential change in the voltage of the capacitor is equal to minus R times capacitance divided by the differential change in time. Okay. So at this point, it's not going to do us any good. We have to get these components on the top. So we're going to have to take the inverse of each side. So this is 1 over VC multiplied by the differential change of the capacitor's voltage. So I got that in the screen. All right. So 1 over VC multiply the differential change in the voltage of the capacitance. And that's going to equal negative 1 over R times C multiplied by the differential change in time. So we've taken the inverse of each side. So we still haven't changed anything. We're still right here. So what we're going to do here is we're going to integrate. So we're going to integrate both sides. And when we do the integral, or the antiderivative, we're going to get rid of these differential chunks. That way we can actually do something with this thing. So we're going to integrate negative 1 over RC over time. We're going to integrate that from 0 to our maximum discharge time, which we're going to call tau. And, or T, we're going to call it T. And on this side, we're going to integrate from Vs, because when we charge this capacitor up, this capacitor will be equal to Vs, so that's our starting point. And we're going to integrate that to Vc. Okay? And so now we have to do the antiderivative of these individual units. The antiderivative of 1 over x is